Now let's talk about continuous random variables. So when is a random variable continuous? If it can assume any value from one or more intervals of numbers. So let's look at some examples. The market share for a new product can be any number between 0 and 1 or 0 and 100%. So that's an interval, so that's continuous. The height of a male can be, let's say, I don't know, between 20 inches and maybe 9 feet tall, I don't know, 108 inches. But you could be any number, not just 21 inches, 22 inches. You could be 21.5, you could be 61.5553 inches. The time it takes to process you at the airline ticket counter, that could be anything between 1 second, 5.8 seconds. It seems to me it's like 600.5 seconds for me, if I'm lucky. And the definition of the longest line is the line that I'm in. Okay, so how do you describe a continuous random variable? We had the probability mass function for discrete random variables, but that doesn't work for continuous random variables. A continuous random variable is described by a probability density function, or PDF, not like Adobe PDF. Okay, the height of a PDF tells us the relative likelihood that a continuous random variable assumes different possible values. So what are some properties of PDFs, or probability density functions? Then we'll look at two examples. First of all, a probability density function must always be non-negative, just like a probability. The total area under a probability density function equals 1, and this is so important. If you want to get probabilities for a continuous random variable that is between A and B, you take the area under the probability density function between A and B. So let's look at two examples of probability density functions. Again, courtesy of Palisades at-risk package, we have some nice graphs. Suppose market share is equally likely to be anywhere between 0 and 1. So the PDF would have the same height everywhere. That's called the uniform PDF, because it's equally likely to be anywhere between 0 and 1. Now the area under this, if the height is 1, it's a rectangle. The area is 1 times 1, or an area of 1. And probability is area. So what would be the chance your market share is between 20% and 80%? You would take the area under this rectangle between 20% and 80%, and that would be 0.6, or 60% area, because the base would be 0.6 and the height would be 1, and the area of a rectangle is base times height. Now suppose you look at the height of an American male, which follows basically a normal random variable, which we'll talk about later, on average 69.4 inches. So the density will look something like this. You'll see more about this later. But basically, what fraction of American men are between 65 and 74 inches tall? Well, that would be the fraction of the area under this probability density function between 65 and 74. It's about 89%. Okay, and again, the density function gives you how dense can mean not very smart, but here it means massive, or how massive is the probability. If you look at the density at 66 inches and the density at 69 inches, basically 66 inches has roughly half the density of 69 inches. This density curve has really roughly half the height at 66 as 69.4. That means roughly half as many men are around 66.1 inches tall as around 69.4 inches tall. Now, one thing you have to understand about continuous random variable. Suppose I ask you the chance of a man being exactly 6 feet tall. So I would always ask this to my class, and a bunch of hands go up. Well, basically, nobody's exactly 6 feet tall. You could be between 5'11 and a half and 6 feet and a half, and you consider yourself 6 feet tall. But to be exactly 6 feet tall, you need to be 6.00, lots of zeros, feet tall, and nobody is really exactly that feet tall. See, if you look at being 6 feet tall, the area of a rectangle with a base of 0 is equal to 0. So that's why nobody can be exactly 6 feet tall. So for a continuous random variable, the chance of assuming any particular value is 0. That's not true for a discrete random variable. In the next video, we're going to talk about a related topic, independent random variables.